So the next speaker comes from Intel Labs. His name is Abhijit, and he's going to talk about Agile formal equivalence verification with Chisel. So in case anyone else was also wondering what FEV stands for, I figured out the F and the V, but not the E.
Hi. So the topic of this talk is Agile formal equivalence verification, which are two kinds of things that you may not expect go together very well. And the idea here, I think, is quite simple and quite modest. And it's based on the observation that some changes that you make to your design are easy to verify. Others are really hard. Typically, we don't know if they're easy or hard to verify when we make them. So all we do is just run the same simulation suite, regardless of whatever change we're making. And the question here is, can we do better? And can we do better by using formal tools? Now, there's two assumptions here. One is that if I have a behavior-preserving transformation, it doesn't actually change what my circuit does, but maybe it changes how it's represented, or maybe it changes the quality of results that I want to get with my synthesis backend. And the second assumption is a bit tougher to meet, which is that the I/O and the state elements remain unchanged. Now, if I meet these two restrictive assumptions, it turns out that I can quickly prove formal equivalence using combinational formal equivalence tools. And the challenge is really figuring out when these assumptions hold. So what can we do along these lines? And to answer that question, we need to put it in the context of a methodology. So the methodology that we are applying here is Agile hardware design, and of course we're using Chisel. So as we know from our favorite paper, we're implementing feature by feature implementation of a design. We're not waiting for the whole design to be implemented before we go through the various stages like verification, tape-in, validation, and so on. Once we implement a feature, there's going to be many opportunities for us to not change the behavior, but change the way that that feature is implemented. So an important thing is refactoring for reuse. Chisel, as we've heard many times today, allows for fine granularity reuse, and we want to leverage its capabilities. We want to rename signals, we want to extract common code, we want to add in a parameter and have some Scala code that generates some Chisel constructs. We may also want to manipulate the quality of results. We can do this based on back-end feedback, or we can have some estimation passes, as we've heard today as well. And we can manipulate the design either by hand, manually, or by invoking different fertile passes on the design. So the context here, again, is Agile hardware design, and we are making a lot of small changes. And it's good to make small changes, but it's also good to verify those small changes. So based on this initial idea of context, what I'm suggesting is that we manually classify a subset of the changes we're making as being behavior preserving or not. And this might be just a simple thing like in your source code management system, you say this particular commit is not really changing the behavior from the previous commit, and so I put a little label in it. So that's one part of it. Now for the verification part, how do I gain confidence that these behavior-preserving changes are actually preserving the behavior? And here we run into the standard issue where verification must be both fast and comprehensive. The time we take for verification cannot be much greater than the design or implementation time, and we have to get high coverage. So we can accomplish this with simulation or by formal techniques. With simulation, we can get incrementally more comprehensive as we simulate more and more cycles, or we might go to FPGA and simulate a lot more cycles after we pay a non-trivial compile time cost. With formal equivalence, it's always comprehensive, but sometimes it's fast, and sometimes it suffers from state explosion. So what do we do here? And the simple thing that I'm proposing is that we add a formal stage along with our unit testing with a timeout. And the question now becomes, sure, you can add this stage, but most of the time you're going to time out, and so it's not really going to be useful. And that's what I want to spend the rest of the talk on, is some examples that show that it can actually be useful, can actually complete in a very short amount of time for the kinds of fine granularity changes that we care about here. And then what do we mean by formal equivalence verification? We're talking about equivalence verification at the Verilog level with two options here. One, we can have a Chisel driver that operates on two Chisel modules and says module A must be equivalent to module B. Or we can have a separate script that operates just at the Verilog level on two lists of Verilog files that can be populated by the fertile code emitter. And what we're doing is invoking a commercial FEV tool with a standard script of commands for customizing it. I'm not talking about any design-specific constraints here. We're not adding properties or anything like that. And I'm not adding any Chisel-specific customizations either. So this is a very simplistic sort of black box view. This is a tool, I can invoke it, and it'll give me an answer or it'll time out. So I want to present two use cases here, and both of them are a bit more complex than the simple kind of thing. So the simple kind of thing would be take a line of Chisel code and put it into a common utility class, and then you can call that everywhere instead of rewriting it. That would be the simple kind of thing. And what I'm talking about here is going to subsume that, and you'll see why. So let's talk about fertile passes first. As I already mentioned, we can have modifications to a design that are carried out automatically in fertile passes instead of by the designer. And today, by default, we have this thing called low fertile optimization, which spits out Verilog eventually. And I decided to try something by removing several of the stages or transformations within this. Now, I don't know if it's legal to remove these things in this particular order. For instance, this constant propagation, which was number 7, might cause a bunch of issues. I know if I remove it earlier in this sequence, it gives me error messages saying you cannot do this. But when I removed it here, it was fine. So now, I want to see if for my specific designs this would cause any problems. And if this new sequence consisting of 1 to 6 and 8, maybe it's not optimal, but is it going to give me correct behavior? So I called this min, and I tried it on the Soder design, which you can download and also try out. And I tried 4 options: flattening it, not flattening it, and using this min pass or using the default Verilog compiler. And I tried it for the 3-stage core, the 5-stage core, and the Ucode core. So the I/O didn't change, regardless of these passes, or flattening. The number of flops in the design also didn't change, and this is, remember, exactly what we want. The lines of code in the Verilog that was generated did change by around 10% or so. And then I'm recording two time numbers here. One is code gen, which is invoking SBT, going from Chisel to Fertile and Fertile to Verilog, and flattening it if necessary, or doing this min pass if necessary. And the other is doing a pairwise FEV on the resulting Verilog code. And this includes things like, reading in the Verilog, getting a floating license from somewhere, and also parsing it. So this is wall clock time. And basically the message here is that it takes 2 or 3 times, maybe 4 times as long, in some cases, to generate this RTL code than it does to formally prove that it's equivalent to some other related code. Another problem might be that you want to take some legacy RTL that's been in your design for a long time, and you want to move to a more Chisel-y way of doing things, and So you want to take it module by module and move it over to Chisel, and then maybe you want to add parameters and make it more usable. But you want the whole system to work the entire time. And this, even though I'm presenting it second, is the problem that I started out with at the beginning. So the legacy RTL characteristics are that it is silicon proven. And at the company I work for, that means something, and that gives it a high level of trust. Even though it may also have very sparse documentation and no unit tests, which was certainly the case for the IP I was working with. So there's a low understanding combined with high trust, which is a bad place to be in. And again, this is because I'm looking at a module at a time, right? I'm not looking at the entire IP block, for which there might be a lot of documentation and a lot of unit tests, and a lot of IP level tests. But for the module, nobody really knows how the interface between this module and its neighbors, for instance. So my Chisel conversion goals were, let me translate first and then focus on abstracting, refactor the hierarchy as needed, and eventually add these parameters to generalize. And I'm looking at 3 modules here in this table. One is a reduction tree that has a lot more inputs than it does outputs, and sort of flops near the inputs. The second one is a combination of muxes and multipliers, essentially. So there's a lot of control that's happening, and that's digested inside of this module. And the third one is a data repacker, which takes data that is relatively compressed and combined together, and then unpacking it into sort of its constituents. And apologies, but I can't talk really more about what these things do. And I wanted to focus on 3 different aspects here, which I've highlighted. One is that there's a big difference between the Chisel and the flattened Verilog code that I get out, especially for this first example. And that's because I have a lot of duplication here. So both the original Verilog and the Chisel are much smaller than the flattened Verilog, which is what you would expect. And the reason that I am flattening this code is to just make it harder for the formal equivalence tool to find any correspondence or regularity in this design. And even still, I think we get a fairly reasonable ratio of code generation time to FEV time, which is a 10 to 150 kind of ratio. For the muxes and multiplication block, the hard part is multiplication. So this is something that combinational formal equivalence tools struggle with at times. And in this particular tool, in my standard script, there's an option to handle multipliers, whatever that means. And so this causes some of the other numbers to be a lot higher. In this case, it actually helps significantly to bring this FEV time down to about a minute. And finally, with the data repacker, what I want to highlight is that just the code gen time with the many, many lines of Chisel that we have is much higher than the FEV time. So those were 2 simple examples, and then 2 simple extensions. One is retiming. Retiming is a programmatic way of getting state differences between your original design and your derived design. And most of the commercial tools out there have support for it. So you can just say, I am retiming my design this way. And then that will be reduced to a combinational equivalence problem. It will be fast. As one of my co-authors, Steve, alluded to earlier, we do have a fertile retiming pass that we can use alongside this kind of equivalence checking. And finally, it's open source tools. I really wanted to use Yosis with ABC. It turned out that it was not able to parse the legacy RTL for the design I just talked about, but that should not be a limitation if you have 2 Chisel modules. So I've not gone back and tried it. My only comment there is that the focus here, I guess, is the heuristics within these commercial tools that allow them to find correspondences and quickly prove equivalence, not necessarily on the solvers. And I do not know how open source tools will handle these. So to summarize, I made 2 sort of assumptions here. We have a behavior preserving transformation. The IO and the state elements are remaining unchanged, and then we said we can quickly prove formal equivalence. And I suggested two things. We're classifying some changes as behavior preserving, and then running this formal equivalence verification. And the takeaway message here is, if you lower the barrier to fine granularity verification, then you encourage fine granularity refactoring, which is what we all want. Thank you.
Thank you very much. We're kind of out of time, but if someone has one quick question, we could squeeze that in. Okay, thank you. Oh, you have one question? Yeah, sure.
So how hard was to ensure state matching designs? You said that's an assumption. Was it because of the tool that you use for equivalence checking, or was it any other reason?
The tool I was using for equivalence checking was a combinational equivalence checking tool. I did not try using the more,
sequential.
like Jasper Gold, for instance, that you talked about. I did not try using that.
Right, there are other tools which can handle sequential.
Absolutely, there are, yes.
Okay.
Okay. So the next speaker is